Hello students. So our today's topic is solving the linear programming problem. In the last video, we have formulated the linear programming problem. Now we will solve the linear programming problem by one of the method that is called graphical solution approach. Before I move to graphical solution approach, let us understand what are the other methods also. So number one is graphical solution approach. Then there is a method called simplex method, which is an analytical tool to solve using the solver. Also, we can solve the solver software in Excel. We can solve the linear programming problem. There is another method called transportation method. It is an application area. We will focus on transportation method also. So transportation method and then assignment method, job assignment, mainly job assignment method in some industry. So these are the four methods out of which we will take up the graphical solution method in greater details. So let us start with the graphical solution approach. Now, for graphical solution, what we do in the first step, we formulate the first of all we formulate the objective and constant functions, which we have done in the earlier video. So we have to formulate the objective and constant functions in terms of decision variables. So that is our first step for the graphical solution. Second step is that we will draw the graph with one variable on the horizontal axis and one on the vertical axis. Say we are having an equation 2x1 plus 4x2 is equal to 5. So we'll take x1 in x-axis and x2 in y-axis and we'll draw a straight line. As you know, it's a linear programming. The function is linear. So we will try to draw some straight lines. Next, we'll plot each of the constraints as if they were lines or equalities. So whether it is an inequality or equality, we'll convert them into equality and we will draw this as straight lines in our graph. So, and then we will try to point out which one is the feasible solution space. The feasible solution space is that space which is bounded by the constraint and the axis. Axis means x-axis and y-axis. As it is evident from coordinate geometry that there are two axes, x-axis and y-axis. So x-axis the equation is y equals 0 and y-axis the equation is x equals 0. Now, so these two equations will be always there, and in addition to this, we will try to add the equation of straight line, say line 1 or line 2. Generally, there are two constraints, so we'll draw the constraints, these two straight lines as constraints. Our next step is circle the potential solution points. Now, what are the potential solution points? Potential solution points are those points where the straight lines that we have drawn intersect. Now there will be a point where these two straight lines, the constraints that we have drawn, they will intersect at one point. That will be one intersection. Now each straight line will intersect either the x-axis or the y-axis. That will also be a point, visible point. And origin we all know that the coordinate point is 0 0. So there will be 4 or 5 feasible points. This is called the points. So these are the potential solution points, and out of which one will be the optimal solution. But first we have to find the potential points. So now it can be a case of, we'll see a maximization case today. Now next, in step 6, we have to substitute each of the potential solution point values of the two decision variables into the objective function and solve for z. That means we have our objective function z equals in terms of x1 and x2. So in that we have to It is called testing. We'll put the value of x1 and x2 for all the feasible points and we'll test the value of z. Now for that point for which the z will have the maximum value is called the optimal point. That point is called the optimum point. So say, step 7 is select the solution point that optimizes z. That means that point, for that point, intersection point, the value of z is maximum is called the optimum solution. So these are the 7 steps. So in our problem, we will, if we just see what was our equations, just I will go and see what our equations were. So this was our objective function, max z is equals 10x1 plus 15x2. This is our objective function. So here we have to put the x1, x2 point, and these two are our constraints. 2x1 plus 4x2 is less than 100 and 3x1 plus 2x2 less than equal to 80. So these are the two constraints and this is the objective function. So now we will plot them in a XY diagram, or what is popularly called coordinate geometry or coordinate diagram. Okay, now let us come to the x and y axis. So instead of y axis we have taken x2. It's all the same. So this is the x1 axis and this is the x2 axis. Now we are having two equations, as you see, that 3x1 plus 2x2 is less than equal to 80, number one, and 2x1 plus 4x2 is less than equal to 100. So we have to plot these points one by one into this xy diagram or x1 x2 diagram. So we will put x1 equals 0 and we'll get the value of x2, and we'll put x2 equals 0 and we'll get the value of x1. So we will get 2 points. We'll get 2 coordinates. I will plot those 2 points and we'll draw the line, which is this line. If you just follow my cursor, this is the line called 3x1 plus 2x2 less than equal to 80. Next, there is another straight line, 2x1 plus 4x2 is less than equal to 100. So here again in the same way we will put x1 equals 0 and we'll get the value of x2, and we'll put the x2 equals 0 and we'll get the value of x1. By this we will get the 2 points, and we have drawn, if you see my cursor, this is the straight line of the 2x1 plus 4x2 is less than equal to 100. So we have got the two equations. We have plotted the two straight lines. So straight line number 1, straight line number 2. Now let us define the feasible region. Now if you see this region which is made blue, which is in the color blue, is called the feasible region. Now you can see this feasible region is bounded by 4 points. Let us see one by one. So if you see, this is the point 0, 0. This is, as from coordinate geometry we know, this is the point 0, 0, and this is another point. Okay, so, and this is another point, the intersection of this line with the y-axis and the intersection of this line with the x-axis. So these 2 points, and there will be another point which is the intersection point of line 1 and line 2. So this is called the intersection point. Now as we know from algebra that if we solve these two equations, we will get the intersection point. So this intersection point, if we solve, is x1 equals 15 and x2 equals 17.5. So this is the coordinate of this point. So we have got our 4 points in the feasible region, number 1, number 2, number 3 and number 4. Now we will put the value of all these 4 points and we'll test the value of z. So if we put all the value, you can see if we put this point is x1 equals 26.67 and x2 equals 0. So if we put this, the z value is 266.67. If we put the coordinate of the, say, origin, then this is also a, we'll get the value 0 obviously, because 0 0 if we put, we'll get 0. And this point x1 equals 0 and x2 equals 25. So if we put this coordinates in the maximization for objective function, we'll get z equals 375. But if we put this point, the optimal point, that means if we put x1 equals 15 and x2 equals 17.5 in the objective function, then z is equals $412.50. So you can see if we compare all the 4 z values. So here it is 0 in this point. In this point it is $375. In this point it is $266.67, and in this point it is z is equal to $412.50. So this point is the optimal solution, where x1 equals 15 and x2 equals 17.5. So that is our, so now see, we have got our decision variable. We have solved for the decision variable, that x1 is equal to 15 and x2 is equal to 17.5. Now, as I told you, there are 2 application areas, that is transportation method. Now, what is transportation method? This method can solve a special form of LP problem, including the classical transportation problem with this typical characteristics. Now you can go through these characteristics. There will be m sources and n destination. Number of variables is m into n. Obviously, if it is a matrix of 3 by 2, then there will be 6 cells. Okay, if there are 3 source and 2 destination, then the cell will be 3m into n, that is 3 into 2 is 6. The number of constants is, in this case, m plus n. So constants are for source capacity and destination. Cost appear only in objective function. Objective function is to minimize total cost of shipping. Now see, transportation is that linear programming where we minimize the total cost. If you see in the last problem, we maximize the cost, but in transportation we minimize the total cost. Okay. There is another application area, that is assignment problem. Let us understand what is the assignment problem. So if this is the method which can solve a special form of LP problem, including the classical assignment problem with this typical characteristics. What are the characteristics? Number 1, it is a special case of transportation problem. The right hand side of constraints are all 1. The sign of the constraints are obviously equal to, rather than, less than, or greater than. Here we write equal to, we don't write less than or greater than, because there is a concept of equal to here. And the value of all decision variable is either 0 or 1. So these are the characteristics of the assignment method, and that's all about the linear programming.